This is homework 1 solution session. Well, the problem given is to find SNR at the output of this given AD conversion system. The given input has peak-to-peak 1 volt sinusoidal signal with a frequency of 1 megahertz. And it first goes through this capacitive amplifier with signal gain 2, right? And then that amplified signal will be sampled by this simple switch and capacitor network with a sampling frequency of 100 megasample per second. And then that sample signal will be AD converted with an ideal ADC. So what that means is that we do not need to consider the quantization noise or whatever noise is, right? Because it just changes analog signal into digital with infinite resolution, we assume in that way. And then that signal goes through this ideal digital low-pass filter whose cutoff frequency is 25 megahertz. So what this means is that, well, we do not have gain, just unity, and then its cutoff frequency is 25 megahertz with a brick wall shape. Okay, so in this system, we want to find the output SNR. Well, in order to find SNR, well, signal power calculation will be quite easy, right? Because we are given 1 volt here, and that signal will be amplified by twice, and then goes through just sampling and ideal AD conversion. And because the signal frequency is much lower than the sampling frequency and ideal low-pass filter's cutoff frequency, we can tell that 1 mega will just appear at the output with 1 mega frequency, but amplified signal, right, by gain 2. Okay, then the problem will be calculating the thermal noise given here and here, right, at this point, right? Because ideal ADC is given, and ideal low-pass filter is given, the noise will just go through it. But of course, it will experience 25 megahertz cutoff, right? So the task is to find the noise power spectral density at this point. That will be the most important problem. Okay, how can we calculate that? Well, we are given this input referred, this operational amplifier's input referred noise power spectral density, and the value is given here, right? Then this noise power spectral density will be amplified by this non-inverting amplifier configuration from here to here, right? In non-inverting amplifier, we know the gain is 1 over beta, right? Beta we can easily calculate. We have here C2, 2C2, C2. So beta will be 1 over 4. So the gain from here to here, if we think it is just a signal, then the gain will be 1 over beta. The voltage gain will be 1 over beta. So the power gain will be 1 over beta square, right? That's what we already know. So power spectral density of this guy will be amplified by 16 times at this point, right? So let's see. The output noise power spectral density here will be 16 times, right? So given is this one, so power will be amplified, power spectral density will be amplified by this much. Then what is the bandwidth of this system, right? Well, we know how to find the closed loop amplifier's bandwidth. Closed loop amplifier's bandwidth is the same as the open loop unity gain bandwidth, right? Okay, so we have here this guy. We assumed that this one is a single stage amplifier with infinite output resistance, which means it works like a ideal integrator, and its GM value will be 4 milliampere per volt. Then and then also the given condition is like this: sample holder load is 1 picofarad, and older guys like these ones are much smaller than C sample holder. So the load seen from this side will be just C sample holder, right? So the unity gain frequency of this amplifiers, I mean this open loop amplifiers configuration will be what? GM over C and 1 over 2 pi, right? So the unity gain frequency of this amplifier can be found here by this calculation, right? GM1 over GM in over C load capacitance in what is that? Radian per second, right? So in frequency hertz, we need 2 pi here, 2 pi, and because we found FT unity gain frequency, and we already know the beta of this amplifier, we can draw one of beta line, right? Then this point will be the unity gain, unity loop gain point, because this is a open loop gain and this is 1 over beta, so the difference is 1 over the difference is a beta actually. So at this point, the difference is 0 dB, so unity gain, right? So this amplifier's bandwidth is calculated to be beta of t, and its value is like this. So this power spectral density will experience with this single pole low pass filter like this, right? And then we will have another low pass filter here, RC network. If you calculate, then you will see that its value is 100 megahertz. So at this point, what we see is that the amplified power spectral density will first experience this low pass filter, right? And then what? We see another low pass filter with this 100 megahertz bandwidth. And for simplicity, I gave us I gave a statement that if we have two pole, well, because we have one pole here and another pole here, eventually what we're gonna do is what we're gonna get is in terms of signal, right? We will see first pole in this entire network, right, up to here. We will see first pole by this one. So the signal is going to start drop, right, from this point. And then here at this point, we see second pole. So its behavior is going to be like this. But for simplicity, I mentioned that let's just assume that this one is like the first a single pole system determined whose pole determined by the dominant pole, right? So ideally what we have, simply what we have is this one pole system, right? So effectively the bandwidth, because low pass filters bandwidth is wider, I'm sorry, lower than this amplifier's bandwidth. Let's just take this one, okay? So the amplified power spectral density will be filtered by this frequency, okay? And then of course, because of this sampling, the sampled noise will be aliased while keeping the same total noise power, okay? So effective bandwidth is 100 megahertz. And then we can calculate total noise power, not power spectral density, by simply multiplying the power spectral density and noise bandwidth, right? So we have power spectral density here, and then the bandwidth, signal bandwidth is FLPF 100 megahertz, and we need pi over 2 for noise bandwidth, right? When system is single pole and when we have flat noise power spectral density. So from that calculation, at the output of sampling, we have 2.5 nanovolt square noise power, right? Even if we do not sample, if we have just only resistor, R switch, we still have the same total noise power, right? Because we are doing sampling here, all the power here will be aliased below 500 megahertz, right? So below 500 megahertz, by this operation amplifier, we have this much total noise power. And another thing we need to consider is thermal noise by this resistor. But we already know when we have 1R and 1C system, the total noise power, regardless of sampling, will be determined like this. And again, because the signal is sampled, this power would be also within this range. So we can simply, because they are not correlated each other, these two noise sources, we can easily add them, right? 2.5 nanovolt square and 4.1 nanovolt square. So entire noise power within this range will be 6.6 nanovolt square, right? So at this point, what we see is this. Of course, the signal is going to appear here, right? Because we have gain 2. This peak will correspond to the amplitude of 2, right? It's not amplitude. Amplitude is actually this much, right? So this much will be 1 at this point, right? Amplify the signal. Okay. And then what? We have low-pass filter. So if we apply this low-pass filter with 0 dB gain, then, well, actually I need to draw low-pass filter like this, right? 0 dB. Anyway, if this part goes through the low-pass filter, then what we only get is this much noise, half of the earlier, entire noise. And signal, because it's within the low-pass filter's bandwidth, signal stays there, right? We know the signal gain, and then the amplitude will be 1 volt here, and that's power is 0.5 volt square, right? And total noise given here is 6.6 nano, but now we have half band. The low-pass filter with half band of this range. So the noise power will be just half, 3.3 nanovolt square, right? So SNR, we calculate here, is going to be just the ratio, this one and this one. So SNR can be calculated like this, 10 log signal power over noise power. So we get this result.